today we are going to see what is the binary tree and what is the binary search tree, and then we will see different operations over the binary search tree like search operation, insertion operation, and then we will see different traversal, how we can traverse a binary tree in order, post order and pre-order. After that, completing this theory part, we will see the implementation in the Python. We will do the coding in the Python. Hello everyone, this is Sharda from Go Hub Technologies, and I would like to welcome you again for this data structures with Python course. And today we are going to see binary search tree and different operations over this. Okay, so am I audible? Can you please confirm me in the chat window? Am I audible, clear and loud? Okay, so let me start now. Previously we have seen general tree. We have seen the implementation of general tree, how we can implement a general tree. I hope you know that we looked at the general tree in the last class, where we went on the tree creation problem. We implemented in the Python a code implementation for the tree. So how you can create a tree in the Python. Okay, let me show you. The last class, I'll do the quick revision for you guys. What do you mean by tree in the data structures? You know, all the data structures before the tree we have studied are the linear, and this is the non-linear. And in this data structure we have certain trees like this. We have root node and then ages keys, and we have certain leaves, and these are the sibling and some internal nodes. And this top node is generally called the parent for it's a child. Okay, and height of tree, you can calculate the number of levels. So levels, this is level 1, then level 2, level 3, level 4, like this. We have certain terms, we know the certain terms related to the tree, and after that we have seen the implementation of this tree. Okay, and then one important type of tree is the binary tree. So what is the basically binary tree? You know that binary tree is basically, we can have at most 2 children. Like a tree that can have 0, or either you can say maximum number of children is 2. That is the binary tree. I hope all of you know what is the binary tree. Okay, and now I'll explain you one of the special version of the binary tree. Okay, that is the special version of the binary tree is binary search tree. Okay, so you know why we need the binary tree and why we need the binary search tree. Okay, can you answer this question? Why we need the trees? I told you in the last classes. Some people are still joining. Guys, there was some request from some students. That's why we kept this batch weekend. In every Saturday, Sunday, we will do the classes for this batch. Okay? So be prepared and always revise the last classes, whatever we have done in the last classes. Okay, it is little bit related to the last class. In the last class we have done the recursion, because recursion also useful when you are going to do the implementation of the trees. So we know till now, we know the recursion, we know the basics about the tree. Okay, let me write here. Okay, we will create a tree, simple tree. And one more important thing, you know the sets. What is the set in the Python? Basically, set in the Python is for getting the unique values. So we can use the sat also for the implementation purpose. We can use sat from the Python for implementing this. Like I can create a tree here, 10, okay? Okay, sorry. Okay, so here I'm creating a tree. Here should be every node has at most 2 child nodes. Like I have this 12, I have this something 20. Okay, and then I can create here some value like 8, and here I can put some value like 50. Okay, and then here I can put some value 30, and here 40, and this I can have some one child 18. So basically this is a binary tree. You can say binary tree is has at most 2 child. You can see this node having only the one child, 30 having only the one child. That's okay, we can have one child, but the maximum we can have 2 childs. Okay, now come to the another type of tree, that is the binary search tree. Okay, binary search tree, BST, I am writing BST. Okay, it is a special type of binary tree. You can say special version of binary tree. First we will understand the concept, then I'll go to the implementation part. We will see the in order implementation, then insert and search in the binary search tree. Okay, like I just want to create a tree that have left child always have less value than the root, or right child always have greater value than the root. And one more property, BST have always unique elements. You can say no duplicates. So you can see, is this binary search tree? Like in this tree, root is 10, and you can say here left is 12. 12 is greater than 10, so it's not a binary searched. Because in the binary search tree, left child always should be less value, having less value than the root node. Okay, I think now it should clear. And what happens in the binary search tree? In the binary search tree, we always, when we are searching, like in this tree, if I just want to search an element, what I can do? I have to search, I have to go for every element. But when I using binary search tree, that time I just want to search an element. I'll create a new binary search tree here. Okay, let me create it. I'll create a binary search tree, BST. And in the binary search tree, I'll search for certain elements. Like here, I'm writing 12. Okay, this element is 12. Then always in the left side, we should have element value is less than the 12. So here I'm keeping 10, and in the left side of this 10 should be value less. So here I'm keeping 7. And here I'm keeping value greater than 10. That is, I'm taking here 12, sorry 13, it's unique. I'm keeping here 11, okay? And then in the right side, the element value should be greater than the root. This child value should be greater than the root. So here I'm taking 25, okay? and in the left side of 25 I'm picking 20, and in the right side of 25 I'm picking some value at like 82. Okay, and in the right side of this 20 value should be greater than this 20, so that is I'm picking here 23. This is the binary search tree. Always left child have value less than the root. Every element of this left child, these should having value should be less than 12, and in the right side value should be greater than 12. Now I just want to search element. How to search element in BST? I just want to search 11. Okay, then what I need to do here? Initially I'll search for 11 in the root node. I'll search if root is less than, equal or greater than 11. So I'll search root is equals to 11, no. So next what I will check, left child is value is greater than root or not. Let me write again. First I'll check value is equal to this value. Here I'm taking a variable value. Value equals to 11. So if value is equals to root, then I'll return. Otherwise value is greater than root or value is less than root. Two possible conditions. If it is greater than root, then what we have? We will go in the right side. Go in right child. And if it is less than, then we will go in left side. So every time we are eliminating half of the tree. Okay. So here you can see 11 is less than this. So first I have done this search. Then I'll come to here. This is 2. Again I'm checking if 10 is equals to this 11. No. 10 is less than the 11. 11 is greater than the 10. Then I'll go to the right side. So here the third search. So in the 3 search, in the 3 iteration, like I'll done only the 3 iteration and I got my element, that is the 11. Okay, and if I'll do the linear search, how much iteration I have to do? N number of elements, but here only 3 iterations. So what I have done here, I gone to the 12, went to the 12, then 10 and then 11. So every time I am doing half of this tree. So initially I have how many elements in this tree? Total number of elements in this tree is 8. So first time 8 elements, then if I'll go in the left side, then only I'll traverse remaining 3 elements. Okay, so search space is reducing, and if I want to see the complexity of this, are you getting the things? What I just want to tell you, I just want to tell you the search complexity. Search complexity for binary search tree. Okay. So search complexity is, you can see here, I have done 3 iteration. And what is the 3 iteration is? If I'll write log 2 of n, n is here 8. So you can say log 2 8, that is equals to 3. So you can say complexity of this is log n. And if I'll do the linear search, then complexity is order of n. And here complexity is order of log n. So less complexity. Okay, similar thing I'll tell you the insert operation, how we can do the insert operation in binary search tree. Are you clear this? What I am doing, actually I am doing here, first we got there what is the tree, binary tree, and then binary search tree. You know, binary search tree always having the left child value is less. It is a special type of search tree, and here always left child having less value than the right child, and right child always having more value than the root. So basically root is always greater than left and less than right. Okay, and then what we are doing here, we just want to search an element. We want to search an element from binary search tree. So if you search an element, it will always first check out the element value is greater than root or less than root. If it is the greater than root, then we will go in the right side. If it is the less than root, then we will go in the left side. We avoid the right side. Okay, so and complexity is log n. Now see the another operation, that is the insert operation. Okay, in the insert operation, I just want to insert one more element. I just want to insert a value, like I just want to insert here 12. Okay, let me open one more pen. Okay, here what we will do, we will see the insert operation. Okay, in the insert operation, I just want to insert a value 12. Okay, how we can insert a value? Similar thing we will do here. We will search first, like we will search the place where we want to search, we want to insert an element. Okay, so here first we will see the new element is 13 that we want to insert. We will see what is the appropriate position for the 13. We will see root value is, no, it's, I'm not taking the 13, I'm taking 10, or I can take the 13, it's okay. 13, so what I need to do, I need to go in the right side. Okay, right side, again this 25 we are taking, for the 25 value is less, so we have to go in the left side of this. Okay, and then we taking 20, so again we will go for the 20 in the left side, and there is no child in the left side of 20, so we will add our 13 here. Okay, and this is also take the order of log n. Okay, similarly for the searching we have different algorithms, like we have DFS, we have PFS, breadth first and depth first. So here what we are doing depth first search. We are doing depth first search. We are going in the depth, not in the breadth. So in the depth search, what we will see in order, pre-order and post-order. Different traversal we will see with the help of depth first search. Okay? Like for this, I'll make the another. I need to create one more tree. Okay, so here the 12, and this side I'm taking 10 and 7. Okay, and here I'm taking 11. Again I'm making the same tree. Values may be some different. 20, and then less than 20 is, I'm taking here 15, and here 18, and here some value 22. Okay, this is a tree. Now I just want to write it's in order, pre-order and post-order traversal. You should know what is the traversal. Traversal is we need to traverse each and every element. Okay. So in the in-order traversal, what we are going to see, the rule of the in-order, first we will traverse left child, LC, I am writing here, and then we will traverse root node, and then we will traverse right child. This is the process for the in-order. Similarly, for the pre-order, what we are doing, we always pick root first, then left child, and then right child. And for the post order, we always traverse left child, then right child, and then root. There is one similarity you can see from all three. What we are doing, we always traversing left child before the right child. So order is, we only changing the order of root. For the in order root, we are traversing root in middle, and for pre-order we are traversing root first, and for post-order we are traversing root in last. Only we are changing order for the root, and this is always same. Like here also we are first, like order of left and right is always left is first and then right. This is first and then this is second. Here also left is always first and right always after the left. And root position is changing in order, so you can remember easily. Like root is in order. If I talk about the in order, then we always read the root in middle. Like first what we will do, left child, then root, and then right child. If I talk about the pre-order, it means root I have to pick first. So root I am picking first, and then I am picking the left and then right. And if I talk about the post order, then root is always last. So what I need to do, I need to pick first left child and then the right child. Here we will write the in order, post order, and pre order of this. So in order of this tree. What is the in order? Here this is the left child for the root, and this is the right child. Okay, and for every tree, this is the left child for 10 and this is the right child. Okay, so first I'll start from here. What I need to do in order, left child I have to traverse first. So left child is this one, this complete, and then I come here, again left child is this. So what I need to pick this 7 first, and then root. After the 7 there is no child, so I'll go back, root, that is the 10, and then right child is 11. So now my left child of this element is completed. So now I'll go to the root, that is the 12. Okay, now come to the right child. Okay, again for the right child, what I have to do, in order traverse. So first I'll go to the left child is 15, and then again for the left child there is no more left child, so I'll go to the 15, I'll write here 15, and then its right child is 22. Similarly, I'll traverse this part, then I'll go to the 20, and then 20, and then 80. This is the in order traversal for this tree. Similar thing, if I'll do pre-order traversing, in the pre-order what I have to do, I need to traverse first root. So first what I'll pick here, 12. Then again I'll come to this tree. After the root, what I need to do, I need to traverse left child. So left child here is this one, this complete. In this left child also I have to pick first root. Okay, so root is here 10, and then left child, then right child, 7 and 11. This is completed left child, root is completed. Now come to the right child. In the right child also I have to do the same thing. First I need to pick the root. So root here is 20, and then left child in the 15. Okay, there is 15, I need to pick the 15, then left child, there is no left child, then 22. Okay, and root I have taken, I'll pick the 80. Now if I talk about the post order, okay, what is the post order? In the post order traversal, I will do here, first I'll traverse left child and then right child, left child, then right child, and then root. So this is my root and this is left child. Again for this I have to go to the left child. So this is the ending point. So here I'll write 7. Okay, and after this I need to traverse right child. So right child is 11. Okay, and then I'll need to write the root, that is the 10. So now left part I have completed. Now come to the right part. What is this? This is the right subtree 20, 15, 80 and 22. From the right subtree I also do the same task. First the left subtree. In the left subtree there is no more left. Okay, so I'll pick the right. So right is 22 and then 50. Okay. For the 20 we have traversed left child. Now we will traverse right child, that is the 80. And now we will pick this root 20. And then we will pick this 12. I hope you got it. Okay. In order, pre-order and post-order traversal. We have taken one example and you should remember these rules. In order, we always read this root in middle. For pre-order, root is always first. And after this root, order is always same, like left child always first and then the right child. So in order, first left child, then root and then right child. Pre-order, first root, then left, then right. And for post, left, right and then root. Somebody is asking a question, what is order of log n? Yeah, Nasir Hussain has written the answer, that is the time complexity. How much time this program will take to execute. Okay. So basically these are the different traversal, how we are traversing a binary search tree. Now we will see the implementation part of this. Like we will do the implementation in binary search tree. Okay. So what we need to do, we need to write a code. So let me start Google Colab. Okay, I'll start the Google Colab. We will walk over the Google Colab. Okay. So here I'll open new Jupyter notebook. Okay, it's opening. And in the description of this video you can see link of a implementation code, okay, that I'm going to explain you. We are going to do the implementation of that part. Okay, like what is basically binary search tree. So in the binary search tree we will create a tree and then we will add some childs, then we will search for an element, and after this we will do the in order traversal. Okay. So let me write here code. We will create a class binary search tree. Okay. Tree node. This is my class, and inside this class I'll define a constructor. Okay. We will define a constructor def. You know that in the general tree implementation we have done all these things. So I hope you know that. Here I'm writing self comma data. I'm creating a constructor for node for creating the nodes. So here I'm writing self.data equals to data. Okay. And then self.left equals to, I'm picking here none. Okay. And they would be max 2 childs only, no? So it's left and right. At most 2 child we can have in the binary search tree. So this is creating the nodes. Now I'll define another function that is for adding the childs. Okay. And inside this function, what I'm writing here self comma data. Okay. First we need to check out if that data is already available or not. Like one property of binary search tree is it cannot have duplicate values. Let me quickly revise you. There are the certain differences between binary tree and binary search tree. Okay. So binary tree is basically non-linear data structure. Let me write here. Difference between binary tree and binary search tree. Okay. So you can say binary tree. Here I'll write binary tree, and in the right side I'm writing BST binary search tree. You know binary tree is non-linear data structure. That we know very well. And binary search tree it is also non-linear data structure. But it is a special type of tree. You can say special version or particular version of binary tree. Or you can say it is some shorted tree. It is always unordered. There is no order in the binary tree. So it will take more time for the insertion, you can say for insertion and deletion and for searching. It will take more time. And you know binary search tree is basically it is a shorted tree. Okay, or you can say it is ordered. So it will take the less time. You have seen that is the login for search and insert all these operations. Okay, and here one rule is always root node is greater than left child and less than right child. Okay, and no duplicates. Okay, these are the thumb rules you should know. Okay, I hope now you should clear. Now we will do the implementation. So we have created here the constructor that can have data and left node and right node. Initially we are initializing left node is none and right node is also none. Okay. Then we are defining here add child function. And inside this add child function we are going to write certain conditions. Like first is it should not contain the duplicate nodes. So for this I'll write a condition if data, first we will check data equals to self.data. Okay. Node, if any node, the value which we want to add already exists, then we will return. Okay. So you can say node already exists. If node already exists, then we will terminate. We don't add that. Okay. This is one condition. Another condition I'm writing here, like where I need to add, in the left child or in the right side. Okay. So I need to check out if value is greater than the root and value is less than the root. So here I'll check if my data and that is self, initially I have self.data. Okay, so I need to compare this data with the self.data. If data is less than self.data, then where I will go? I'll traverse left. I'll go to in the left side and add the element in the left side. Okay. So here we need to go in the left side. But again in the left side, I need to check out the conditions. If there is more elements available, like two conditions I need to write. If left child is already existing, okay, like here self.left. And one condition I have to write is else, means no left child, like you are at the end. Two things happen, like what happens here, first we are comparing with the root node, okay, and if it is the root node then we will return equals to the root node, we will return. Now we are writing the more conditions. Data is less than, like we will go in the left side or in the right side. If data is less than the self.data, we will go in the left side. In the left side, we have to traverse the complete tree until unless the leaf node. So what happens, one condition is self.left, means there are the more left elements. In the left side, there are the elements. Until we have elements in the left side, we will do certain task here. And else condition is, means there is no more left child. Okay. That means we will add this node. So here what we will do, self.left. In the self.left we will call this binary search tree node. We will create an object of this. And here we will pass data. This will add node to the left leaf, last left leaf node. And here I need to write the condition. What condition I have to write? Just think about it. I need to recursively call. Means I have to traverse complete left side. So here I need to write self.left. You know recursion, right? Dot add underscore child. Recursively we are calling this add child function. One possibility, are you getting the things? What we are doing here, basically first condition is for if node is already exists. Second condition is for the left side. Like if data is less than the self.data. Then we will go in the left side And in the left side there would be two possibilities. One is the leaf node, and one is we have to traverse the complete left nodes, all the left nodes. So here I'm writing this condition, self dot left means until we will finding the more left nodes, then here with the help of this current left node we are calling add underscore child, this function recursively. Okay, and in the else part, self dot left equals to, we are adding this node to the last leaf node, binary search tree node. Same thing, this is for the left side. Same thing we have to write for the right side also. If you have any question till now, you can ask me, because this is very important concept, like how to add an element in the left side. Okay, and similar thing we will do for the right side also. We just want to add element in the right side, then what we will do? Right side. Okay, here I'll write the code. If data is greater than self.data, then what the condition I have to follow? Okay, here I have to write two things. If self.write, okay, then we will call recursively add child. Self.write dot add underscore child. Okay, and in the else condition we will add to the right child. Self dot write equals to binary search tree. Got it? Same thing I'm doing here for the left and right. Okay, or otherwise I can keep this in the else also. Like in place of this, I can write else, this upper F. Okay, this would be the better. Okay, one condition is for this and then left, and this is for the right. Got it? How to add nodes in the binary search tree. Okay, same thing we will do for the search. I just want to search an element, or otherwise first I'll see this part. I'll write the implementation part here. I'll call these functions. Okay, here I'm taking a list. Okay, numbers equals to some values I'm taking here, like 16, 5, 1, 20, and then here I'm taking one more value. Certain values I'm taking in the numbers. Okay, and then I need to write one more function, that is for building the tree. Okay, for building the tree I need to write one more function. Def build tree. Okay, and here I'm passing elements. Like I just want to create a tree from this list. You can say here, you can write numbers. Any variable name you can give. Okay. And then here, print. First we will print elements. Print tree elements. What we will print? We will print numbers. Okay, as it is. Then we will create a tree with the help of these numbers. Root equals to, we will create an object of binary search tree node. Okay, and we will pick the first element as a root node. Okay, so numbers and 0. And then here we will write a loop for all the elements. Like first element we have taken as a root. Okay, and then we are writing here a loop for I in range, and inside this 1 comma length of numbers. Okay, and then here root dot add child. Numbers of I. And what it will return? It will return root. Okay, this is for building a tree. Now we will build a tree. Here we have called this add child and bind a search tree node. Add child, this function we have defined. So now we will call this function like tree equals to, okay, build underscore tree, and inside this I'm passing numbers. Okay, and let me print tree. This is the simple binary search tree we are going to create. After this, we will search an element and we will do the traversal of this binary search tree. What happened? Build. Is this function name difference? Build tree is not defined. Okay, this is should be outside the class. Yes. Yeah, we cannot print this tree, no? For printing, I have to write one more function, but basically you just try to understand what I'm doing here. I'm just calling this add child inside this. And add child will automatically, what would be the root node? Root node is 16. After this add child will get the number, like it will get the 5. Then it will check 5 should be in the left side or right side. Okay, it should be in the left side. Then for the 1 also it will check the left side, and for 20 also left right. It will insert in every element. And we are getting the root from here. Okay. Somebody is asking a question, ma'am, we have to pass parameter self, right? Yes, we have to pass the self. Okay, no, self inside. If you are defining a function inside the class I have defined two functions. One is the init